Okay, I think we can start with the last session of this conference and the second lecture by Enrico Valdinoci.
So thanks a lot. I'll continue discussing a bit the topic of non-local minimal surfaces. Well, people who know me know that I'm very optimistic. I always plan to do many things, so probably I won't do as much as I planned. But I would like to present a feature of non-local minimal surfaces, which I find very amusing. This was discovered with Serena and Ovidiu, and it's a phenomenon that we call the stickiness. And I will it's a very general phenomenon, and I won't give a precise definition of it, but we will see it in some concrete examples that I think are quite instructive. But before diving into that, let me review a bit the final observation I did yesterday about non-local mean curvature and classical mean curvature. So the non-local mean curvature was defined for a sufficiently nice set E. You take X on the boundary of E, and HS X is up to dimensional constants that I now forget. This is the integral over Rn of chi tilde E y x minus y n plus s dy, and s was our fractional parameter between 0 and 1, and chi tilde was minus 1 in E and 1 in the complement of E. And we said, okay, this looks like a strange definition for a curvature, but actually it's not that strange if we believe that we have to review what we have learned in classical mathematics, because also the classical mean curvature happens to be equal up to constants to, I think, the limit as r goes to 0, 1 over r, the average of the normalized characteristic function in a small ball. Okay? So this, I think, is very nice because it allows us to uh, basically bypass the algebra related to the mean curvature and focus on the geometry. So a set has a positive or negative mean curvature, even in the classical case, because nearby we see more the complement of the set than the set itself. And for example, suppose that you have a corner. So suppose that your set E something like this, like a heart shape if you want, and say, suppose that this is the origin. Uh, well, H, so this is the set E. H at 0 is minus infinity. Well, this is maybe questionable if you work with classical definition of mean curvatures, because you are supposed to take derivatives, but you cannot take derivatives here. But the advantage of thinking the mean curvature is in this integral form is that, actually, let me change a bit the picture because this looks 90 degrees. I don't want to be so specific. Any angle would be fine here. Just I'm taking more than 90 degrees is also fine. Okay, so something like that. So if you use this definition, well, you just have to look at a small neighborhood here and look for cancellation. So let me point out, maybe let me draw a bigger picture because okay, so I take a small ball, but I draw the ball sufficiently large to be seen. And I look for cancellation. So this is a cone. Basically, what happens is that the normalized characteristic function is -1 here, -1 here, -1 here, 1 here. Okay? And then I cancel this contribution and this contribution. So when I'm integrating in this ball, it's like integrating -1 in these two cones, right? But then I get here an object which is -1 times this angle, basically, divided by r. So this diverges to -infinity, and that's why you see that the classical mean curvature is equal to -infinity. Now, the advantage of this is that the same calculation works for the fractional mean curvature, because now I still have the same simplification, and I'm integrating -1, but divided by 1 over the polar radius to the power 1 plus s when you write it in polar coordinates, okay? But or 2 plus s, right? But this is going to give no, sorry, 1 plus s when you write it in polar coordinates, I think. But so this is going to diverge for the same reason, and you get -infinity. Okay. So far so good, but your impression is that so at this level, everything looks pretty much the same, right? It's -infinity in the classical case, -infinity in the fractional case. So what is the difference? What is the benefit of considering the fractional mean curvature instead? Because I promised that the non-local world was somehow beneficial or advantageous in some situations. Well, there is, I think, an exceptional benefit, because if you take now this point here, let me call it P, well, in the classical case, h of P is 0, simply because I lie on a flat segment, for example. But in the non-local case, if I have to make an educated guess, Hs of P is strictly negative. The reason being that if I do the same computation averaging in small spheres, well, sooner or later, if P is sufficiently close to the origin, okay, here in my picture, P is sufficiently close to the origin. Of course, if I have to make a serious computation, I have to rigorously check what I mean by sufficiently close, right? But just a proof by picture, if P is sufficiently close to the origin, when I average out, I still see this conical singularity. So it's not a singularity anymore because I'm away from the singularity of the kernel, so I get something finite, plausibly, but something negative. So in a sense, I have a stronger, if you want, notion of preservation of the sign of the non-local mean curvature that is not what happens in the classical case. And we will see that this plays a role. Okay, so the question that I would like to present now is what happens at the boundary. So boundary behavior of non-local minimal surfaces. So let me be very, let me propose very simple examples. So my domain omega will just be a slab in R2, so I consider 0, 1 times R. This is a subset on the plane. And I consider an external datum to be a nice graph. Basically, this is my reference domain omega, and outside omega, I put a nice graph. And then I look for the S minimal surface with this external datum. Now, the first fact that we proved with Serena and Ovidiu is that the graphical structure is preserved. This doesn't look like a graph, more graphical. Okay. So if the external datum is a graph, then the S minimal set is also a graph. Or by graph, I usually mean subgraph. So situation like this, this is the external set. And here inside, I expect to have some graph. And the natural question is, how does this look like? And the game that I will propose to you is a police investigation. We look for all possible suspects and we rule out the ones that are impossible, right? If they have an alibi, they cannot be the culprit. The culprit is the S minimal graph. And if we have only one suspect without an alibi, even if we don't have a strong evidence to, to proceed, we deem that as the culprit, okay? This may happen in real life, so why not in mathematics? So the graph the external graph that I propose to you is the following: 0, 1, and then let's just take some straight line outside, something like this. Even symmetric if you want to have a very simple case. Right? So outside I'm like a cone, and I think the subgraph for consistency, and what I expect to be the S minimal graph corresponding to it. Well, the first guess I would say is proceed as in the classical case. In the classical case, you don't really care about the external datum. You say, well, the segment joining 0 to 1 is the shortest path. So this is the classical minimizer for this configuration. But this has an obvious alibi, because if I compute the S-mean curvature at this point, the S-mean curvature is negative. Okay, so, and the reason is that when I start averaging out ones and minus one, nearby I have a perfect compensation, but once my sphere hits the external datum, I see more -1 than 1. Okay, so this is not possible, and I rule it out. Okay, second possibility. Which at that time was actually our first guess. So a very uneducated guess, I would say nowadays, but at that time we thought, well, maybe it's non-local, right? So you feel more the external datum and you try to follow it closely. So looks like pretty much a parabola, maybe. Of course not. Why not? It's even worse, exactly. It's even worse because if you compute the mean curvature here, you can do exactly the same. Now, it's even worse because even locally, you see more -1s than 1s. Okay, then third possibility. Okay. Well, maybe you bend up. So you do something like this, but then you bend up. Because now, if you try to do the same here, you average out, so nearby you see more ones and less -1s, but when you go far away, you see the other way around. So maybe, you see, when the situation changes, maybe you have compensations between -1 and 1. But this is also not a minimizer, because you don't need to compute the S-mean curvature here. You could do the calculation here. And here, the same situation as before, because take the horizontal plane, well, all the part below the horizontal plane counts as -1. The part above the horizontal plane counts maybe like 1, maybe like -1, but so that you cannot have a full compensation. So also in this case, the S-mean curvature here is negative. So what we have learned with this example is that it's pointless for me to keep drawing examples that produce a local minimum, because at a local minimum, I can always touch the graph from below and get a contradiction just by averaging with respect to the half plane. So next level is to say I have to bend up. So something like this, and then I bend up. Because now if I compute the S-mean curvature here, again, I have locally a predominance of 1 over -1, but then I have a predominance of -1 over 1. Maybe I get 0. But this is not the case for this picture as well. I don't know if you see where I can get a contradiction. At the corner, exactly. So at this point here, I can take, doesn't count, you are an expert though, but yes, at the corner. Because now I can look at this plane and say, well, all this, sorry, this half plane is full of -1, and I will not be able to compensate it with the other half plane. Well, strictly speaking, I cannot compute exactly at the corner the equation, right? Because the equation is something that you have in an open set. But if you're not too picky, you can say, well, so what? I will compute it here, and this will be somehow my limiting argument with a limiting half plane, and then I push the, the picture towards the corner. I mean, but this is an argument I will keep using, that I will try to compute things at the boundary, maybe as limit of things coming from inside. Whenever I'm able to do that, I will try to speak about the boundary equation. This is a tricky part. We will see it why, but this picture, I would say, is convincing and rules out this possibility. Well, then there is only one case remaining. And once you have eliminated all the possibilities, the last one, even if it looked unlikely, must be the right one, at least according to Sherlock Holmes. So the only remaining suspect is something that goes up and then bends up. And yes, here you see if you compute things, you may have compensations. You cannot make the argument here at this corner, because you cannot reach this corner from the inside, right? So you need to compute the mean curvature at points from inside. So if you are lucky, maybe you can reach this point, but not this one. So you're not allowed now to take the half plane passing through this corner. And this is interesting because you have here a jump discontinuity. So non-local minimal surfaces, even in the best possible scenario that you are, for instance, in the plane with a very nice datum, which is even a graphical structure, happen to present jump discontinuities at the boundary. And the example is actually even more striking than that. So in the paper with Serena and Ovidio, we had a number of examples. I think that the one that is more impressive to me is the perturbation of the half plane. So I will not write the formal statement. Again, I will draw a picture. So the picture is the following. So suppose that your external datum is a half plane. Okay, well, if your external datum is a half plane, your S minimal surface is a half plane as well. This is not completely obvious. This was proved by Caffrey, Rockjoffre, and Savin. And to prove that, you need to prove first a maximum principle, to say that if your external datum is trapped in a slab, then the S minimal surface is trapped in a slab as well. And so since you can shrink the slab towards a line, this entails that the non-local minimal graph in this case is just a horizontal straight line. But then what happens if you perturb it? So suppose that you put a couple of small bumps here and here. I mean, these bumps can be as far as you want and as small as you want. Suppose that the height of this bump is, say, of order delta, then what happens is that the corresponding non-local minimal graph is discontinuous at the boundary, so it's smooth inside. It arrives with a vertical tangency, but then it has a discontinuity of order delta to the beta. Well, beta depends on S, and it's larger than 1. And actually, it diverges when S goes to 1, so this gap becomes smaller and smaller. So I think that beta of S goes to plus infinity as S goes to 1. So don't believe too much in my picture. The picture is probably too emphatic because delta to the beta is much smaller than delta, of course. And beta goes to infinity as S goes to 1. So this becomes smaller and smaller and smaller when you recover the classical case. Okay, so well, what I presented was actually the way we bumped into this example. If you want to prove it, it's another story. Unfortunately, the proof is more technical, but the idea is relatively simple. So the idea of the proof is to construct a barrier. To construct a barrier, we need to put something here to lift it up, okay? Well, strictly speaking, I'm not supposed to touch this point because this is a boundary point, so I will have to put the barrier slightly inside and then push it towards this corner. But as we did before, we somehow skip this detail and we just try to lift the surface at this corner using a barrier. Okay, and the barrier is like this. So suppose that I start here. So this is 0. This is 1. And I will construct my barrier somehow piece by piece. I start with something which is completely flat here. And moves up here. Well, when I do this, I know what happens, because if I compute the S-mean curvature here at the origin, the S-mean curvature is infinite. But if you remember, I also said, well, the S-mean curvature is infinite at the corner, but remains negative here. So you have a small segment in which the S-mean curvature remains negative. And then I have somehow to glue things. So this is the hardest part because I have to bend this barrier back. And this I have to do it carefully. And we didn't have a very smart way to proceed. We really took a power-like function because we could compute things. And then we interpolated with straight lines because we could compute things. And we put all the pieces together. So the computation is horrible, very long. But then you have an object that looks like this. Actually, if you zoom in, the barrier is not that nice, so the zoom in of this part would look like something, a power, then a straight line, then a power, then a straight line, then a power, or something like that. Okay, so it's a little bit piecewise smooth. It's not that nice, but just to have an idea. Now, when you do this, you do things carefully. You somehow maintain the fact that HS remains negative in a region. Okay, so if you're careful enough, you choose your parameters, you prescribe this height here, say eta, and then you manage to get a negative mean curvature up to a certain point. But here on the top, we know that HS has to become positive because if you have a picture like that and you compute the S-mean curvature on the top, now you have a full half plane of ones which cannot be compensated from the bottom. However, you can estimate this contribution on the top, and you will find that it depends on eta, of course, and it's like a power of eta. So you can now put a bump outside and say also here, just to keep things nice and symmetric, you don't really need to put the two, but it's nicer. Now, if you take this bump of order eta to some 1 over beta, so a small power of eta, you will compensate this positive curvature. So now at this point, when you add the bump outside, this curvature, which was order of eta to the 1 over beta, is compensated and becomes negative. And so now you have constructed an object that is like has this shape and there's negative curvature in 0, 1. And then you can use it as a barrier because you could put this object here and push it up. Now you have to choose eta, right? But you choose eta to the 1 over beta equal to delta, so that when you push this object from below, so this would be now your barrier. So this is the construction here of the barrier. Does something like this. Something like this. Well, and I know, strictly speaking, I have to reduce a bit the barrier to avoid the corners to be inside the domain, but I skip this detail. And then I push it upwards. And when I push it upwards, I will remain always below the datum, because the datum is larger than the bump here. And so by maximum principles, this is this as a negative mean curvature. I cannot touch the minimal surface, the S minimal surface inside. And so the S minimal surface has to be above this barrier. Since this barrier has a discontinuity here as a jump that is like eta, that is like delta to the beta, the proof is complete. Okay, so and then in the paper we had a number of examples, but one may wonder, okay, these are just pathological examples. In many cases, you don't expect stickiness. In fact, it's the other way around, because later on, we proved that stickiness is generic. Again, what we mean by this, I will not give a formal statement, but I will make a convincing claim. So, take again your set omega to be 0, 1 times r, for instance. Take a nice external datum. And suppose that for some miracle, the S minimal surface corresponding to this datum is continuous at the origin. This may happen because we know, for instance, for the half plane, that is the case. So there is at least one case in which you don't have stickiness. So maybe there are others. In principle, we cannot exclude that. But then if this is the case, you can add to your graph an arbitrarily small bump, arbitrarily far, and the result is that the corresponding S minimal surface now will have a jump discontinuity at the origin. So arbitrarily small bumps produce stickiness. Now, how do you prove this? Again, the proof is very technical, but it is based on some simple ideas. Well, the naive idea would be that you use the original picture as a barrier. So you may argue, I take my blue curve as a barrier when I add the little bump. Now, if I don't have stickiness, I will compute the equation here and get a contradiction, simply because whenever I have, this is a bit related to Serena's talk yesterday, so it's sort of a maximum principle. And the maximum principle, when you have integrals, is even stronger, because if you compute the equation and one set is included in the other, well, the contribution coming from the part of the set between the two surfaces will produce a positive integral, and you get a contradiction. Okay? So the only reason for which you cannot compute the S-mean curvature at the corner is that the corner is not reachable due to stickiness. Okay? So rough idea, use the unperturbed S minimal surface as a barrier for the perturbed case. Then, in principle, you have something like this, right? So you have the original datum, the original surface. Then, by contradiction, you have the new surface, which is not sticky at the origin. So that's something like this. But then when you compute the S minimal curvature at the origin, you have all this part let me call this region, I don't know, A, that is in the perturbed minimal surface, but not in the original one. So if this is the little bump, let me call the original one E0. Let me call the perturbed one E. When I compute HS of the set E at the origin minus HS of the set E0 at the origin, well, all contributions here disappear. I only have the contribution coming from the little bump, let me call this B, and A. So I have the integral in Rn. Then in E, I have A union B. But then this is strictly negative because this function is -1 in A union B and 0 otherwise. Oh, no, sorry, this is just the characteristic function, I think, of A union B. Yes, maybe with a factor 2. Because this is 1 in one case and -1 in the other, or maybe a factor -2. Now, this doesn't really work because, as I was saying, okay, so this is a contradiction. The contradiction is saying that I cannot compute the S-mean curvature here because I don't reach this point. But then if I don't reach this point, it means that E is discontinuous at the boundary. End of the proof. But there is one catch that in principle I don't know that I can compute the S-mean curvature exactly at the boundary. So I have to either exclude the boundary touching or to be able to pass the equation to the limit. Ideally, I would prefer to exclude the boundary touching, but it's probably exactly what I cannot do, right? Because nothing prevents, in principle, that the surface E is above E0 and then has the same tangency exactly at the boundary. So I don't have an obvious way to avoid this pathology. So I have to show that I can compute the equation at the boundary. So to make this work, one needs to be able to say, to pass the equation to the boundary. So passing the equation to the boundary means that I can compute the equation along the surface, but if I have a boundary point which is reachable by a sequence of points coming from inside, the equation must be valid at the point itself. So this is somehow a regularity theorem, if you like, because you have an operator, which is the S-mean curvature, and you want to say that the solution is more regular than the number of derivatives of the operator itself, right? When you can pass the Laplacian to the boundary. Oh, if the function is C2 up to the boundary, right? Or C2 alpha up to the boundary. C2 to the up to the boundary would be enough, but C2 is not a good space for PDEs, right? So the only way you can prove that you can pass something to the boundary is to strictly beat the regularity of the operators. That's a fact of life, I would say. You never prove that something is C2. I don't know any proof that has an integer types of regularity. And but so you have to use the same idea in this case. So I have to beat the number of derivatives. And now, of course, you say, what you mean by derivatives? It's an integral operator, so I don't have derivatives. Yes, but in a sense, the scaling of the integral operator I wrote is like 1 plus s. So the S-mean curvature is whatever it means of order one plus s. So the classical mean curvature for me is of order 2, because if you write it in coordinate, it's like the Laplacian plus blah, blah, blah. So it's an order 2 object. This, if you write it in coordinate, you can do it, and you see that you have some kind of weighted averages of first derivatives, and if you count just the exponents, is of order 1 plus s. I mean, now, if you don't believe that, if you think that this is just a heuristic argument, what I mean is the following: that if you can prove that a surface is C1 alpha with locally C1 alpha with alpha strictly larger than S, then this is sufficient to pass the S-mean curvature to the limit. So this would be a rigorous statement. C1 alpha regularity with alpha larger than S is enough to pass the S-mean curvature to the limit point. And then all boils down to prove that the S-mean curvature is the S minimal surface is C1 alpha up to the boundary. This is the case in a suitable sense, in the sense that you can prove that you have a dichotomy. So only two things can happen. So suppose that you have E, which is an S minimal surface, and suppose that it's a graph. Y less than U of X. And suppose that, again, the external datum is nice. So you have an external datum here, U0, which is nice, or at least it's nice near the origin. Then only two things can happen. Either U0 at 0 minus is equal to U at 0 plus, or U0 at 0 minus is different than U of 0 at 0 plus. So either the graph is continuous or not, right? So either you have this situation or this situation. But if you have this situation, so if you have continuity, then let me also call U tilde the total graph. So U0 in minus infinity 0 and U in 0 plus infinity. So if you have boundary continuity, then U tilde is C1 alpha near the origin with alpha bigger than 0. So 1, it's saying that continuity implies differentiability. Once you are continuous, you're actually differentiable across. And actually, even more, you are sufficiently differentiable to pass the equation to the limit. So this would solve our problem here of the barrier. But since it's so nice to have a full dichotomy, let me also mention that if you have, yep, oh, alpha larger than S, sorry. Yes, yes, yes. Alpha larger than S, that's what I meant. So we are using this part of the dichotomy, but it's also cool to say what happens here. Well, what happens here is that you are still C1 alpha up to the boundary, but you have to turn your head. So here, what happens in this case, let me draw the picture, something like this. So you have your U0 outside. Okay. Then you have a discontinuity, so you miss this point here. But then what happens is that locally you are a graph in this direction. So you have to think that this is y equal u0 of x. This is y equal u of x. But actually you are a graph if you look the other way around. So you are also a graph of the form x equal v of y. And now v is C1 alpha as a graph in this direction. So if you want, the curve given by u is always C1 alpha. But it's C1 alpha as a horizontal graph if you have continuity, in this case, and it's C1 alpha in the vertical graph if you have discontinuity. So it's just a matter of using the right coordinates. And now this may look strange because I don't know. Well, it looks strange because it's not the typical boundary regularity theory for PDEs. But the reason here is basically that when you write the S-mean curvature in coordinates, you have an object that is like, if you think about the local counterpart, the gradient of the function blows up when you have a vertical touching point, like the neck of a catenoid. So you have to change your coordinates to see that actually that gradient that becomes infinite is actually 0 in the right coordinate system. And that's why you get this kind of dichotomy. You always get regularity, but in the appropriate coordinate system. Okay, so this dichotomy has a number of interesting effects. So first of all, point one of the dichotomy makes the previous proof correct now, because now the only thing I was using there is that I can pass to the limit if I have continuity. So I have point one that allows me to have sufficient regularity to pass the equation to the limit at the origin. It also has another cool byproduct. So the dichotomy implies that stickiness is generic because it makes the above proof correct, but also implies for free a butterfly effect. That is arbitrarily small perturbations make the boundary derivative switch instantaneously to infinity. Let me explain this by picture again. So you have a situation, take your u0 and take, for instance, a horizontal derivative. You don't really need this, but just to have an extreme case. So if you don't have stickiness, then not only you are continuous at the origin, but you are actually C1 alpha through the origin. So here, u prime of 0 is equal to 0. But then we know that I can put an arbitrarily small bump here. Then in this case, I do have stickiness. But then if I have stickiness, I use now point 2. And this means that V is C1 alpha, so V prime at this point is 0. But since V is the inverse of U, this means that U prime at this point is infinite. So you arrive here with a vertical tangency. So the picture is now this, and now this is U prime of 0 equal to plus infinity. So an arbitrarily small bump make the derivative switch from 0 to plus infinity. So that's why we called it a butterfly effect. Okay. So the only thing remained is to prove the dichotomy. Proof of the dichotomy is again quite involved, but it has a number of simple ideas. So well, the proof of point 2 relies, so point 2 relies on a work by Caffarelli, Da Silva Savin, which is about the obstacle problem for non-local minimal surfaces. So you have to think somehow that the case 2 is a case in which the domain is an obstacle for the surface itself. And in that case, they proved that you have a C1 alpha detachment from the obstacle, but then this means exactly that locally in the coordinate frame given by the normal of the obstacle, which is in this case is this vector here. So the obstacle problem for this case would be that the domain itself is the obstacle, and you have a C1 alpha detachment from the obstacle, which is exactly the fact that V is C1 alpha. Point one instead requires an ad hoc argument. So point one, yes, point one would be the case in which you have U0 from outside and some U from inside. And you know that U is continuously agreeing with U0 at the origin. And so the idea is that you do a blow up. First of all, you do a blow up and you reduce to cones. Okay, so U0, for instance, in this picture is very flat. So when you blow up, you would just have the horizontal line. And U in this picture, when you blow up, to me looks like something like this. Now the blow up is not completely trivial because typically in the literature, the blow up procedures were done in the interior. So even to do the blow up, you have to work a little bit because first of all, you have to prove a boundary monotonicity formula. Well, the boundary monotonicity formula, we couldn't prove it, but we could prove it with the remainder, which means that when you do the blow up, you actually have to do two blow ups to make it homogeneous. But this is a technical detail. I would say that at this level, you may think that there is an appropriate monotonicity formula that allows you to blow up and get, in the limit, a homogeneous minimizer. So a minimizer with a conical structure. Now, minimizer now in the half line. Okay, and then what you do? You would like to exclude exactly this picture. This picture is your enemy because you have continuity but not differentiability because you have a corner at the origin. And how do you exclude it? Well, you construct a barrier. So you have to poke your nose here. To poke your nose here, you have to put your nose in the right direction. So the barrier is something like this. If I remember correctly. The barrier has this shape, and you have a big nose here. So I want to put the nose in the origin, so something like this. And the corner of this nose is higher than the corner of the blow-up. So if I put the nose in the origin, I will violate the maximum principle. So the only thing I have to be sure is that I can construct an object like this shape, with negative mean curvature. Okay? And again, the parameters are chosen in a way that I don't touch the solution outside. That's why I drew this part here, right? This part here stays below this straight line. This part here stays below the x-axis, so it's not really going to occur. So when I mean, what I mean by hs less than 0, well, only in the active part of the nose, so only in this region here, which may touch my original solution. And how do I do that? Well, again, it's a horrible computation, but you have the faith that it can work, because you remember the previous trick of saying that here hs is minus infinity. So maybe if I adjust parameters in a careful way, I'm capable of saying that the negativity of hs is preserved by this kind of corners here. So I mean, this work is not it's not straightforward at all, but then you can put your nose in the origin and lift the slope of the solution. But this means that the only admissible slope for the solution is the vertical one. So from this you get that the slope of the blow-up is infinite. Well, it could be plus or minus infinite, but let's say I do it from this way, I have plus infinite. Okay, so this is not the end of the proof, because the only thing that you can say in this case is that if you have boundary continuity, then you u tilde may yes, okay, so sorry, I forgot to mention. Okay, you have two possibilities, right? Either the slope is plus infinity, which is allowed because you can put the nose with an arbitrarily steep nose, or actually the slope is 0. The slope can be 0, in which case the touching of the nose would not violate anything, because you touch at a point in which you violate the mean curvature. So for instance, the top of the nose would violate the mean curvature. Okay, so neither of these complete the proof, because the slope could be infinite just because you have a cusp. So you may have continuity, but with a vertical tangency, and you would not violate anything. Or the slope could be 0, in which case you are continuous and even C1 if you want. But that's not enough for you, because you want C1 alpha with alpha larger than S. So now you have to work a little bit more, because you would like to say that if the slope is plus infinity, actually U is discontinuous. So if you prove this, then you are happy, because you reach a contradiction with the original assumption that you had continuity at the origin. And you prove that the slope is 0, U tilde is actually C1 alpha with alpha larger than S. This would prove point 1. Okay, so how do you proceed for this? Well, the second part, the slope is 0, U tilde is C1 alpha. This is based on an improvement of flatness. But this is something also Serena was saying yesterday, and of course, I think next hour we will spend some time on that as well. Here the situation is slightly different because we have to do this improvement of flatness at the boundary. But the idea is pretty much the same. So if the slope is 0, it means that you can start with an initial configuration that is sufficiently flat, and then you can iterate your regularity estimate and get that you are flatter and flatter on a smaller scale. And this gives you C1 alpha. And the fact that alpha is bigger than S, it's by computation. So you check what is the alpha that you get due to scaling and the contributions from infinity, and you get that actually alpha is larger than S. So it's not, I wouldn't say that it's nothing mysterious except that you have to keep track of all the quantities. Okay, now we have to rule out the worst enemy. So that could be really a conspiracy of non-local minimal surfaces against us, for which you could have a situation like this, that maybe you are very flat from outside, and from inside you have a cusp. This is still our enemy. And this you have to rule out by hands. So you say, well, if the slope slope of the blow up is infinite, you actually have a picture like this with the original set very close to the vertical line. And then this means that you enlarge this picture, so you zoom out. Here's something like this, so 0, and almost vertical. Well, but this allows you to put in this scale balls of large radii, and you move these balls towards the original picture till you touch. And since the ball has a very large radius, this is quite flat, so at the touching points, you have a very flat object touching from this side. And you reach a contradiction. Well, you have to do the calculation, but why do you think you reach a contradiction? Since at this scale, this ball is very large, it's telling me that here I have a large contributions of -1. Sufficiently large. Well, you may be pessimistic and you say, not too large, because you can have almost, or actually even more than half of the contributions here coming from the external side, in which you have 1. Okay? So here, I'm not winning. I'm almost drawing, right? Because I have a very large ball. The very large ball to me is almost a half plane. If I have a half plane, I have exactly half of -1 and half of +1. So with the half plane, I would draw the match. With a large ball, I lose the match, but barely. It's like in Champions League, right? You lose 0-1 the first match, but you hope to win 2-0 the return match. And the return match is played here, because here I have more -1s than 1s. So again, I have to do the calculation, but the return match will be somehow in my favor. When I enlarge the ball, I see more 1s than -1s. Of course, I have to do the calculation, but in this case, again, I violate the S-mean curvature prescription, so I get a contradiction which tells me that that U is discontinuous, and I'm in the first case. Okay, so the only reason for which I don't have this touching point, is that U is discontinuous, right? I only have a touching point if I have a curve in this quadrant. The only reason for which I cannot have a touching point is that U was vertical to start with. So the only way to avoid touching points and get the contradiction is that actually U tilde is discontinuous to start with. Okay, so I may still have 10 minutes, but I didn't do the break, so I could either finish here, or maybe there is a beautiful proof that was due to Luis Caffarelli to rule out symmetric cones in dimension 2. The proof is very short, so maybe I can use 5 minutes to show you if you haven't seen it. And would be a nice way to end this. Okay, so yesterday Serena mentioned that S minimal surfaces in the plane are smooth. And this was proved by Ovidiu Savin and myself. Actually, with Ovidiu, we proved that they are C1 alpha. And then from C1 alpha to C infinity, there is this improvement of regularity that was done by Begonia Barrios, Alessio Figalli, and myself. But before these results, it was not evident what was happening in R2. And so it was natural to try to rule out the possibility, for instance, that the Simon cone in R2 is an S minimal surface. So I will not prove this, but I will prove that if you take E to be the xy in R2 such that x times y is positive, this is not S minimal. Okay, and the proof that Luis Caffarelli thought is very ingenious, and it's only by picture. So take a point, for instance, 1, 1, and draw 2 lines. And now consider the situation in which you remove this cube Q from the set E. So Q is, I think, so if this is the origin, this is 1, this is 1, Q is 0, 1 times 0, 1, and look at E minus Q. Now, you are assuming by contradiction that E is minimal, but then also E minus Q is minimal. And this can also be proved by picture because in the original case, the S perimeter of Q was computed with Q being in the set. So in the original case, Q was competing with the complement of the set. So Q was interacting with A, with B, with C, and with D. Okay? When you compute the S perimeter of E, Q is in E. So it has to interact with the complement of E. So it's interacting with A, B, C, and D. But when you compute the S perimeter of E minus Q, Q is outside the set. So it's interacting with A tilde, B tilde, C tilde, and D tilde. But now you see the interaction of Q with A and B is like this L shape. That the interaction with A tilde B tilde is this L shape. So it's congruent to this interaction. So it's totally the same. You get the same energy interacting this way or this way. And the interaction with CD is this interaction along the diagonal of this butterfly shape, which is the same as if you interact with the C tilde D tilde. So the energy of the original picture, or the local energy if you want to bound it in a large sphere, the energy of the original picture is the same as the energy of the modified picture. So E minus Q is as minimal as well. Okay, but now I compute the S mean curvature of the set E minus Q at the point 1, 1. Now, when I look at the point 1, 1, I have this contribution here coming from C tilde. Then I have this contribution here, this contribution here. Well, in principle, I have also this one, but I can, for instance, blow up at this point, and these contributions are more than this. And HS of this point, maybe if you want after a blow up, becomes negative. And so this is a contradiction. Or even, let me do it a simpler proof that doesn't even need the blow-up argument. Let me compute HS, this is actually easier, E minus Q at the origin. When if I compute H of E minus Q at the origin, I know that when Q was included, the S mean curvature was 0. But now Q is excluded, so this quantity here is actually, so I'm counting less set than E. So it has larger S mean curvature, but this was 0 to start with, and so this is a contradiction. And with this, I think my time is over, and we can have a rest.
Enrico for the beautiful lecture. So there are questions, remarks. Okay.
No, bye first. Well, sorry, thank you very much. This was really wonderful. And I was wondering actually about the stickiness and how does that compare to, this is a physics question somehow, how does that compare to like capillarity problems?
Exactly. So you're right. So on the one hand, it's a form of capillarity, which is induced by long-range interactions. So this is something that doesn't occur for the classical surface tension, but here you are making it possible to lift the liquid in a tube due to the remote interaction with other particles. So I think it's kind of intriguing to think about it in that way. Well, so what we did with Serena and Francesco Maggi is also considering a long-range theory for capillarity. So you can also use non-local minimal surfaces and kernel interactions to describe the capillarity theory. So what is the droplet in a container according to these rules. But it's a little bit different than the capillarity effect induced by the remote interaction here, because when you look inside the droplet in the domain, you don't have the set outside. So there are two different models in a sense. If you're asking whether or not you can check this experimentally, my feeling is that probably not, because my pictures are too optimistic, right? Because I draw delta to the beta but I think that the delta to the beta is very small. So my feeling is that if you try in real life, unless you have something very precise and very expensive, and no one is going to waste money to check delta to the beta. So yeah, I think it's a very interesting point. How much you can lift the liquid just using far-away interactions. Also, you have to get rid of other possible capillarity effects with the boundary of the container. So I think it's a little bit tricky to design an experiment that really proves it, but in principle, why not? Thank you.
It's more a curiosity than a question, but does the same idea rules out also some cones in 3D?
I'm not sure.
At least the stupid ones, like you take not the same picture because it's not the analogous of the Simon's cone even in 4D, but you take the octants and you paint like 4.
I mean, so I think that there are some variations that would work, but you always need some kind of symmetry for which you find congruent regions. So the difficult part for us was that in general, the cone in 2D even could have wild sectors, right?
Sure.
Non-symmetric
Yeah, sure.
and so on. But yes, I think that the idea is kind of general, and we used not the same picture, but the same idea that you can rule out possibilities just because of congruent interactions. So you may say, okay, this is not as minimal for whatever reason, just because I reduce to another picture, which I can check that is not as minimal because it has a protrudent corner, for instance, like in this case. Yeah. Just checking that the energy would be the same, and so you rule it out. So I think it's a cool idea to look at congruent interactions whenever you can spot them.
Okay, and is the real proof of the flatness of minimizing cones in R2 really relying on this sort of...
No,
Okay.
it's completely unrelated.
Okay.
So the real proof, as Serena was saying, is based on a translation idea. So you have a corner, you want to cut the corner. You can't. Well, you could, but the computation becomes too hard. So the naive idea of cutting the corner produces a lot of interactions that are hard to compute and to compare. So the idea is that you move the origin where the corner is in one direction, and you check that this lowers the energy. Now, the problem is that if you draw a picture like this, well, you know where the corner is and you know what is the right direction. where you move the corner. But in general, you don't know it. So you have to use a stability inequality. So you have to say, I don't know where the corner is looking, but I do one step forward and one step backward. So I compute the energy, the original energy, with the average of the two perturbed energy. And this is exactly a discrete stability formulation. And when you do this, well, you have to do the calculation, but what you get is that when you do a step of order 1 and you glue in a large ball of radius r, you have a benefit, an energy benefit in doing so, which is positive. Okay, you can compute in the powers of r, and now the approach works only in dimension 2 because the powers of r are either small or large, because you get 1 minus r to a power. Now that power is, if I remember correctly, n minus 2 minus s, exactly. So when n is 2, 2 minus 2 minus s is minus s. So your gain is 1 minus r to the minus s, which is positive, good. Yeah. But when n is 3, you get 1 minus s. So now this becomes negative and you don't gain much.
Okay, thank you.
Okay, there are other questions? Okay, if not, we thank the speaker again.
Thank you.
Okay, now we have the last lecture of this conference by Anna Skorobogatova. Thanks.
Thank you. Okay. Yeah, now it's working. So yeah, remember that we're, so for now, our setting is area minimizing integral currents. I'll shortly digress to discuss a little bit also these mod Q ones that I mentioned briefly last time. And we finished with this result of Neighbor and Valtorta on the these strata for the singular set that tell you how many directions of translational symmetry you have, that this kth stratum where you have at most k directions of translational symmetry is k rectifiable. And also it comes with, their result comes also with Minkowski content bounds, which I didn't say last time. So yeah, you really have pretty good structural information on these kth strata, but the trouble is that sort of for saying something more generally about the whole singular set, this isn't so helpful if you have these branch points, which are in the top stratum where you have at least one tangent cone that is supported in a flat plane of the same dimension as the surface. Yeah, maybe I'll just say a little bit about what how their rectifiable Reichenberg approach works, which, as I said last time, it's I mean, it's since then been used in a lot of different contexts where essentially you just need this, you need a reasonable monotone quantity that you can use to quantitatively control the flatness at all centers and all scales at the correct dimensional level for whatever, whether it's singularities or nodal sets, whatever you're interested in. So the general philosophy is that you have these beta 2 coefficients, which here they're at the k-dimensional level, which are essentially like an L2 excess for from planes for the like at the level of the singularities. So you look at a center point x in a scale R, and this is the infimum over all k planes L of you need scaling, and you look at the distance to this a plane over R squared, you integrate it with a ball radius R, and you're looking at, I mean, this is the beta 2 coefficient associated to that, in this case, the k-dimensional Hausdorff measure sitting on this kth stratum. And what this rectifiable Reifenberg kind of machinery is telling you is that if you have quantitative smallness of this in the sense of, so it's in the sense of small Carlson norm, basically. So that's saying that if you look at ball radius R of the, now you integrate from 0 to R, this beta 2 coefficient, S squared ds over S d. Again, then if you have the, so there's some delta such that if this is less than, so yeah, if this is less than delta R to the K for all X R, then so this works more generally for general measures, and we're taking the measure to be this guy in this case, basically. So then the support is K, rectifiable. And the powerful thing about this machinery is, I mean, you need to verify this condition. And so, yeah, there exists delta. So you need to verify this condition, but actually you don't need anything about the local finiteness of this measure. And I mean, since then there's been a kind of simplification of this. So there's also a more qualitative version of this by Adsam and Tolsa, where they just ask for there's no for all X and R, they're just asking that this thing integrated over, let's say you fix things in the unit ball, that this thing is just finite. And they characterize rectifiability under this condition, but they need local finiteness of the measure that they're applying this to. And yeah, more recently, there's work of Delelis and Fleschler where they're able to actually boil down to instead of having to go through this rectifiable Reifenberg machinery and verifying this smallness, because you don't a priori know that your measure is locally finite. They show that they have this result that says that if you don't have sigma finiteness, then you can find a non-negligible, purely unrectifiable subset. And then in this context, you can basically, so then it reduces to actually just having to sort of verify the more qualitative boundedness condition that Adsam and Tolsa have. The one drawback is that then doesn't give you the content bounds, but it's still pretty interesting, I think. But okay, so we have this for the strata, but as I said before, our problem is that we have branch points where there exists at least one tangent cone, which necessarily comes with multiplicity because we have Allard that tells you if your multiplicity 1, then actually it's a regular point. And yeah, I mean, these are singular points necessarily. And sort of in general, by this stratification, what you can write in the setting of integral currents, this won't be true anymore in the setting of these mod Q area minimizing ones, but you can in general then decompose your set, in this case, into the top stratum, so like exactly the branch points, complement the m-2. So my claim is that there's nothing in the m-1 stratum. And this is very easy to see by taking tangent cones, because, right, so there's nothing in -1. And this is because there are no singular points that where you have a tangent cone that splits exactly m-1 directions. And this is because right, if you had something like this, then this tangent cone would be an area minimizing cone. It would have a spine of dimension m-1. Then its cross section is a one-dimensional area minimizer. But in this case of integral currents, these are classified as, I mean, there's just a single line with multiplicity. So yeah, because any tangent cone is basically C prime cross up to rotation. And this is a 1D area minimizer cone line. So, right, so indeed, we have, so yeah, the goal will be to get a lower dimension estimate on the singular set. And yeah, this tells you that we basically just have to concern ourselves with the branch point, so this piece in this case. Because, right, by this result of Neber-Valtorta, we know that this is m-2 rectifiable. And in general, so already we saw from these examples of holomorphic curves that these are, in real variables, these are two-dimensional things that already have isolated singular points. So in codimension 1, probably you're all familiar that you have the codimension 7 estimate for the singular set, so it's much better. But in higher codimension, you can only hope for a codimension 2 singular set, precisely, right, because of examples like this. So that's sharp. And yeah, already here we have even the structural result by the stratification. So we just need to understand what's happening here. And then this was the content of Almgren's big regularity theorem, which was precisely to get first a dimension bound, which was already extremely difficult because of these branch points. And so remember, so as I said before, the philosophy should be that anything in terms of regularity that you can hope for minimizers, you can also hope for semi-calibrated surfaces. And so, yeah, this was indeed shown also for semi-calibrated surfaces, the dimension estimate to begin with. Then I'll discuss the structural results. So big regularity. So this was Almgren in the 80s, and then it was revisited and simplified by Deleles and Spadaro in a series of papers from like 14, 15, maybe. And since I'm also going to discuss the semi-calibrated case, so this is for minimizers. And for semi-calibrated, this was the dimension estimate was work of Lucas Polaor in 2015. And it's saying that the Hausdorff dimension of the whole singular set is at most n-2. And so my plan is to now give you some ideas behind how this argument works, and also tell you a bit about I'll first digress a little bit to these mod Q ones to explain how things are different there. But yeah, after that, my plan for the rest of this lecture is to discuss the ideas and also hopefully tell you how one can sharpen this to a structural result. So more recently, this was so for minimizers. This was basically simultaneously proved by Cromwell and Wickramasekura and myself with Camilo de Lellis and Paul Minter. This was in 23, where we're able to get the singular set is n-2 rectifiable. So nothing, unlike the stratification of Neighbor and Valtorta, we don't have anything like content bounds, unfortunately, because you could, so we showed with Gianmarco Caldini more recently that sort of for the top, if you're looking locally around a branch point, then this kind of tells you that you have some integer density that's kind of locally the top one, and then the other top density branch points nearby, you can get measure bounds at least, but that was already not super easy, and we had to essentially use all of the machinery that was used there. And yeah, there's a lot of difficulty with things like lower densities accumulating to higher ones, and also different strata accumulating to things, because each stratum is not closed. The whole singular set is closed, but you can have accumulation of things from lower strata to higher and things like this. Okay, so and yeah, so our methods differ a little bit to what Cromwell and Wickramasekura did. Ours are kind of really closer to following Armgren's original proof, which is why I think it shouldn't be too difficult to sort of along the way explain what we have to additionally do to get to this structure. But yeah, firstly, as I promised, let me tell you about these mod Q area minimizers, which, as I said, so as you can see, you have the singular set here is codimension 2. So it doesn't allow you to see things like triple junction singularities, these like tetrahedral singularities, things that actually appear in soap films. And that's kind of, at least from my opinion, the main sort of motivation for developing this theory of mod Q area minimizing currents, because it's a framework that it still allows you to see this kind of higher multiplicity phenomena of sheets collapsing together, which can happen, but it allows you to see these codimension 1 singularities. So a small digression. Mod Q area minimizers. So here Q is a fixed number. And yeah, yeah, the main idea is that now, instead of having integer multiplicities, we're going to take multiplicities modulo this fixed integer q. So more precisely, we can consider, I mean, you consider basically flat chains mod q, and then so integral currents mod q are, so then you can use this to give a well-defined notion of mod q mass and mod q boundary, and then currents mod q are those flat chains mod q that have finite mod q mass and boundary, finite mod q mass. And so, right, we can, and so to make sense of these things, we do things in this mod q flat topology. So we can consider the mod q flat topology, which you look between two different flat chains. This is the infimum. So you're basically, right, the idea is that you'll take T, you take S, and the mod q flat distance between these two should be how much it costs you to close this up into a boundary, and then how much it costs you to fill it, accounting for the fact that it doesn't cost you anything to add things mod q. So for instance, this is equivalent to 1 plus q t. So in other words, I'm saying that this is the infimum, the mass of R plus mass of W, where R is going to be, so these are m-dimensional. R is m-dimensional, W is m plus 1 dimensional, such that if you look at T minus S, this is going to be R plus the boundary of W plus, as I said, you can add Q copies of anything you like. So this, right, this is my W, and this is these two pieces that I added on my R. Okay, and now, yeah, what I'm taking are equivalence classes in this topology, and yeah, I'm basically taking so my mod q minimizers are representatives in these equivalence classes that have better mass relative to any competitor mod q. So again, I'm not going to write every single detail, but because I'll make it, hopefully it will be clearer from some examples that I give you in a minute. So mod q minimizers, they have, so they're representatives in mod q. This is such that maybe we call this T, such that the mass of T is less than or equal to the mass of T plus any boundary mod Q. So okay, so yeah, so maybe let me immediately give you some examples to make it clearer what these things look like and how you can see things that you don't see using integral currents, precisely things that allow you to have codimension 1 singularities. So examples. So in Q, so the most basic one is if you look mod 3, you take your boundary to be three Dirac masses, and then the minimizer mod 3 with this boundary is going to be precisely the triple junction, And the reason for this is that you're not introducing any extra boundary mod 3 here. So this is kind of these 3 points as an integral current would not be an admissible boundary basically to get anything reasonable. But here you can, right? So here, if you put +1, 1, +1, and here you'd have -3, which is 0 mod 3. And so indeed you can get, you can get these kind of things that you would like to see if you're, really wanting to see sort of soap film phenomena, at least mostly. Okay, and maybe a more elaborate example, which allows you to see that you can have branch points happen, unlike in the setting of integral currents, where for hypersurfaces you can't have branch points. Now you can. So somehow these mod Q minimizers, the phenomena you see is more compatible with like more general stable integral varifolds, basically. I mean, with the added benefit that they have sort of more topological rigidity. So, and coming from this mod Q minimizing assumption, which allows you to still prove regularity results that are much more difficult in the general setting of even for stable minimal hypersurfaces. You often have to add extra hypotheses because you have like annoying things like these like holes appearing near, like where you have like maybe at the level of the tangent cone for the surface, like say a bunch of half planes coming together with some spine, and you'd like to say that sort of the top density points of your surface are sort of really looking like a perturbation of this spine, but generally you can have kind of holes in the top density points, which is a problem. But these kind of phenomena are actually ruled out in this mod Q setting for topological reasons. And it makes proving regularity statements easier, as well as just, I mean, for a start, the fact that we have the minimizing assumption. So when Q is 4, you can have, you can have the following example, which, so you take a plane and you take an ENIPA type surface that is going to lie, so it's going to go above and then below, and then above again, and then below again. And so it intersects the plane, say in this case, in this kind of cross, and in the middle, it meets it tangentially. And to make this, so, right, okay, this, you can, this by itself is just like, let's say a stable minimal hypersurface. To make this really a mod Q minimizer, I mean, you need to add some orientation. And the way we do this in this case is you basically introduce alternating orientation. So this is how things tend to work here, that essentially you'd orient things always towards this cross. So here you'd say point things this way, here you go this way, you go this way, and here you go this way. And so this ensures that maybe let me use a different color. This ensures that the singularities that you have here along this cross, they're counted with multiplicity 4, so mod 4, no boundary. Okay, so they're really interior singularities. And as you can see, sort of what is happening at the level of the singularities here is you have basically this kind of cross singularity with an extra dimension, and it's collapsing slowly towards this point to a pair of planes. And this is really reminiscent of what one sees, for instance, for stable minimal hypersurfaces. Okay, so what can one say in general about the singularities in this case, so let me start with some early results that are already pretty powerful. So, okay, firstly, there's the easy case, which is Q is 2. This is just multiplicity 1 unoriented 1 unoriented surfaces, which means that you just have, I mean, this means you don't have branch points, you just have the n-1, n-2 stratum. So then you get immediately 2 singular set is it's 2 rectifiable. Now, some more interesting cases that were already known for a while. When you look at Q as 3, so mod 3, there's this really elegant result by Jean Taylor from 73, which says that if you look at 2D minimizers mod 3, NR3, the hypersurfaces, the only singularity models you can have are triple junctions, so this cross an extra dimension. And she also gets a perturbative result close to any such singularity, so near any singularity, which is he looks like the following picture. So it's a C1 alpha perturbation of so you have, let's say, 3, you have your triple, you have your cone, and then you have a C1 alpha perturbation of this for your surface. So it looks like a C1 alpha perturbation of the unique tangent cone, which is a triple junction. So yeah, and the kind of goal in general is to generalize this result of Jean Taylor as much as one possibly can, which we have kind of a reasonable partial version of this, even in higher codimension. So codimension 1, one really can generalize this to the level of getting also the perturbative statement at the level of the surface itself, whereas in higher codimension, one can get at kind of the level of the top, like the singular set in the top stratum, but not at the level of the surface itself, because one has higher multiplicities and one can have like classical branch points of lower density than the top one. So mod Q, the highest density that one has almost everywhere is Q over 2. And so, yeah, basically you can have in higher codimension classical branch points of lower density than this Q over 2. But maybe let me just give you the statement in this case of the general result, which is, you can see it as sort of an analog of what happens for so what happens for in the integral case. So a singular set, you have, so now you have, as well as you have the branch points, which are the top stratum, union, the stuff that's in exactly the m-1 stratum, union the m-2. So, right, by Neighbor-Valtorta, in this setting, one has that this is still m-2 rectifiable. Note that in this case, so it's not exactly that we have, even though I kind of said this morally last time, that you should think that you basically have what you have in the integral case plus this extra piece, which is now not empty. That's not strictly true. We kind of don't actually know if we have other. So the point is that we don't have a full understanding of these lower strata. So for instance, even for hypersurfaces, we don't, so I'll mention this shortly, but what one knows for classical, so for area minimizing integral currents, is that in 2D, you have a classification, you have uniqueness of tangent cones really everywhere. This is a result of Bryan-White. And you have a classification that they're always unions of planes. So basically think like a bunch of complex planes meeting at a point. We're missing an analog of this in this setting. So we don't have, and this kind of classification in 2D is the core of sort of getting these structural results where you're able to say things up to, so for instance, this allows one to say, I didn't say this, but as part of our structural result, we also get uniqueness of tangent cones up to HM-2 almost everywhere. And the core of that is coming from what's happening in 2D. And you almost everywhere get the 2D picture across the remaining dimensions. But like here, we don't have a good understanding of this 2D picture. So we don't know what other singularity models other than classical ones, meaning the ones you can see for integral currents are here. Another thing I should mention for this result of Jean-Taylor is that in particular, I mean, it's saying that you don't have, so since the only singularity models for 2D minimizers mod 3 are just the triple junctions, she rules out these like tetrahedral singularities that one can have at the level of soap films. And yeah, so that's maybe the one flaw of the this mod Q setting is that, yeah, unfortunately there are, so yes. Yeah, but that's the only reasonable, because you also have, like for the tetrahedral singularity, you have the triple junctions accumulating. Right. Yeah. But well, I mean, one does have to check that you don't have anything in the zero stratum. Right. Yeah. Right. I guess that's part of the result. No, I mean, yeah, it's incompatible because I mean you can do like a sinc source type argument or whatever. You can check. I don't know. Yes. Yes, exactly. Yeah. But that's, yeah, I guess. But sure. But I guess my point is that if one wants some framework that really allows you to see everything, including this doesn't work for that. That was kind of my only point. But yeah. Yeah, so like in that case, maybe the more reasonable approach is sort of this set theoretic one that I mentioned, which of like Harrison and Pugh, Francesco Maggi, and others, where yeah, you can see tetrahedral singularities, but you can't in this framework. Okay, and so what can one say in terms of structure? Well, here you have, again, m-2 rectifier. So this is in general, so this is arbitrary dimension and codimension. And I'll say a bit about what happens specifically in codimension 1 that allows you to do a bit better. And this piece, that's exactly the points in exactly the m-1 strata. These are locally C1 alpha submanifolds. So you get you do better for this piece and for kind of topological reasons in this framework. because essentially these points locally form a geometric free boundary. And so that's why you can do better than just m-1 rectifiability here. And for the hypersurfaces, you can improve this to get the full sort of generalization of Jean-Taylor's result, can get the perturbative result for the surface itself. Okay, and this is kind of a combination of works of a number of people. So, this combination. But yeah, I mean, roughly speaking, the strategies are rather similar for maybe everything other than this piece, which I'll say a bit about also when I talk about the structural result for area minimizing integral currents, because that appears there, but for a small subset of the branch points. This is Delelis, Hirsch, Marquez. Well, there are earlier works that are by just Delelis, Hirsch, Marquez, and Stuvard, but then there are kind of a number of papers that also towards the end includes Valor. And this is for hypersurfaces, mostly. And for the higher codimension case, oh, and I should also say there's also work of Minter and Wickham-Sekera, where they show using a different approach, they recover the same structural result using Wickham-Sekera's regularity theory. So they observed that as a consequence of that, which is for stable minimal hypersurfaces, you can apply it in this case. So this is also the hypersurfaces. And then together with Camille and Paul again, we do the higher codimension case. Okay, so yeah, but the takeaway should be that essentially the new piece that you get is exactly these codimension 1 singularities. Okay, so now let me go back to sort of the general strategy of Engren and sort of which aspect of it one strengthens to get the structural result. So back to singularity. So okay, so what is the idea? So already we saw that you reduce yourself to just considering branch points. And so you can reduce locally to the setting where you have that your surface T is epsilon close to some plane with multiplicity, let's say in the unit pool, by rescaling. So you're already starting localized around a branch point of density Q. This is an integer. And the idea will be sort of bearing in mind that taking tangent cones are bad for branch points. They don't give you any information. the goal is to perform a better blow-up procedure around branch points where, because, right, what the monotonicity formula for mass ratios is telling you is that you're rescaling like homogeneously in all directions, or isotropically rather, I should say. So like there's no preferable direction. Whereas what you want to do around branch points is basically rescale more in the transverse directions to this to the flat direction. And you want to blow up using a different monotone quantity, which is Armgren's frequency function that I'll tell you a bit more about in a second, which will allow you to get the goal is to start approximating your surface with graphs which have to necessarily be multiple valued in this case, because remember the prototypical situation, if you like, is as always this example of w squared equals z cubed, where you have these sort of two sheets of your surface collapsing onto the plane w equals 0 locally around the origin. And right, and so what you kind of want to do is start approximating your surface with, in this case, it would be a two-valued graph. I mean, in this case, it's exactly equal to this two-valued graph locally around the origin, but in general, we just get suitably strong Lipschitz approximation with small Lipschitz constant for the surface. And then you want to start blowing up these approximations. And okay, the first naive approach would be to do this relative to optimal planes. We'll see that this is, again, not a great idea, because basically the same problem as with tangent cones where everything just collapses onto a single plane with multiplicity can happen still if you try and do this just relative to optimal planes. And so then comes in Armgren's center manifold, which is basically exactly the thing you need to get around this. So the main idea. First, you approximate T with a multiple valued graph over the optimal plane. So here, what I won't write this in detail, but essentially these multi-valued graphs, they're taking values in the space of unordered Q tuples. So they take Q values at once. You can put the L2 Wasserstein distance topology on these things. So you're taking the infimum over all possible permutations of these values, and that's sort of the image space for my functions. The annoying thing with the space is that, I mean, it's a highly nonlinear space, so you can't like add, subtract two different multi-valued functions. The only operation you can do is subtract the average of all the Q values, which is often what one does want to do. Then the next step, once you have such an approximation, is to use. I'll explain in detail at least some of these steps. So we'll use Armgren's frequency function. So this is it's a better monotone quantity. at branch points. And what this monotone quantity is doing, so it's telling you at a given, so I'll write this down in a second, but it's essentially telling you at around a given, so most classically it's used for harmonic functions, and you can use it to get information on like nodal sets of harmonic functions. And what it's telling you around a given, let's say, point in the zero set of your harmonic function at a given scale is the kind of homogeneity of the function at that scale relative to that center point. And it turns out that this frequency is monotone, it's really monotone, increasing for classical harmonic functions in the radial variable, which allows, and the invariant objects for these, so the things that you get as blowups, are homogeneous harmonic functions, classically. And the kind of point is to adapt that classical situation here, with the caveat that firstly, we don't have exactly harmonic functions. We will have these graphical approximations for our surface, and so yes, the linearization does give you Dirichlet energy, so they should, and indeed they are close to being harmonic in a suitable sense, but also they're multi-valued, so that's another thing you have to account for. And yet another thing you'll have to account for in general, so let me first say before I mention that, so let's say you were able to do this, and let's say you could really do this. I mean, I mentioned this problem of doing this relative to optimal planes. Let's say that wasn't a problem for a second. And let's say that in this approximation, you really landed in the beautiful situation where you transform basically the branch points into zeros of graphical. So this is kind of the this is kind of the ideal scenario that we would like. And then you could really, I mean, yeah, as I said, this thing isn't exactly minimizing Dirichlet energy, but in a suitable sense, it's almost minimizing it. But yeah, unfortunately, one cannot hope. I mean, one cannot hope for this in general. I mean, yeah, even forgetting about any other issues of doing things relative to optimal planes already, like you can't hope for really for these things to become zeros, right? You can't hope that they all really fall onto the plane that you're parameterizing things over. But let's say you could get this for a second, then the final step would be to study the linearized case and get a structural result. So study linearized problem of I mean, when I say zeros, I really mean, I mean, it's zeros classically, but here they're really like singularities where all the sheets are collapsing together simultaneously. The singularities of these functions, because my functions are multiple valued, of the multi-valued Dirichlet minimizing functions and their singularities. And so the point is that at this step, so this step you can kind of do independently and it's still useful. It's just we have to, as I said, we'll have to adapt this bit a bit. But yeah, the point will be that you study this case. Here you have a unique continuation type result where you can use this monotone quantity, this frequency function, to tell you so for deminimizers, we have continuation, meaning that either, so you always have the case where everything might just collapse. So remember, these are multi-valued. So one possible scenario is that all of these multiple sheets collapse onto their average, which is a classical harmonic function. So either this function is going to be Q copies of a classical harmonic function, or you have you have a dimension estimate, but you even have rectifiability at the level of the singular set. But I mean, for the purpose of, let's say, the dimension estimate, you just need, and even, I mean, even for the structural result, it's not so helpful having the structural result at the linearized level. It's just kind of helpful for the dimension estimate. The singular set where all of the Q sheets come together is at most m-2. So, right, so you should think of this as being closer to, and like whatever that exactly means, like complex harmonic functions. So it's not classical harmonic functions where, because this singular set is not like, it's not the same as the singular set for classical harmonic functions, which is where they vanish to higher order, and then you have the sort of codimension 1 singularities. Yeah, this is right. Because we're really looking at these multi-valued Dirichlet minimizers, we're interested in the places where all of these Q different sheets come together. But you can, so for this, as I was saying, we want to use Armstrong's frequency function, and dimension reduction. So to take iterated blowups and boil down to the 2D case where you have, well, rather in 1D, you don't have any singularities. And in 2D, they become isolated. Okay, so that's kind of the linearized problem, which one is able to study reasonably well. But as I said, there's a big caveat from passing from the nonlinear problem to the linearized one. Because so what you'd like to then do is say, okay, we have this unique continuation type result that gives us the dimension estimate on the singular set. For the linearized problem, let's try and propagate this back up to the surface itself with a compactness procedure. And that's where things go pretty badly wrong with this sort of, at least with this more naive step that I said. So what can go wrong? Well, let me tell you with another more complicated example of a holomorphic curve. So consider the example WZ, such that W minus V squared Z cubed is Z to the 100. Okay, so what happens here? Well, at the origin, you still have a branch point. So near the origin, the optimal plane is still w equals 0. And here you have that w is like z squared plus z to the 100 over 3. So this is the branched guy, right? This is the kind of, it has this 3-sheeted structure. And in this case, all of these sheets are collapsing onto the graph of this guy. And this is a problem for this sort of more naive blow-up procedure that I mentioned, because what will happen in this case, if you try and just like naively build your, so in this case, you really have even a unique, so as with w squared equals z cubed, you have a unique tangent cone that is the plane with multiplicity 3 now because of the 3 sheets, w equals 0. So here, unique tangent plane with 0. But blowing up using this Armstrong frequency, which remember, I mean, I'm not going to define it in detail because, yeah, it doesn't really matter what the precise definition is, but remember, this is like detecting radial homogeneity. Of like, if you, yeah, the sort of graphical approximation of your surface, or if you like, yeah, the sort of radial homogeneity relative to, like, if you're looking at where all the sheets are collapsing together. Graphical approximation. So if you blow up, if you try and do this blow up procedure that I mentioned using this frequency function, this will give you, in the end, just the graph of this guy with multiplicity 3, which is bad because, right, you want to, I mean, the aim is to propagate this this dimension estimate back up to the surface itself. You want a persistence of singularities, and this is not happening if you do this. So we'll yield the 3 copies of the graph, the graph of w equals z squared. So, right, this is precisely what one wants, and somehow this is no different to, in some sense, the issue that you get with taking tangent cones in the first place, because, yeah, everything is just collapsing onto this super nice regular surface. And so how does one get around that? Well, that's where this Armstrong center manifold comes in. So to get around this, we need the role of Armstrong center manifold is basically exactly to, so if you like, what you're essentially doing locally around these branch points is you want to like Taylor expand your surface relative to the optimal plane. And the point is that what you want this Armstrong frequency function to detect, so it's kind of detecting, it will be detecting basically the first homogeneity relative to this plane in this expansion. And if this first homogeneity is corresponding to a regular term, this is a problem, because this is precisely not going to give you this persistence of singularities that you want. And so what you want to do is basically the role of Armstrong center manifold is to kind of subtract off all of the first few regular terms until you see the first singular one. So the role of this is morally to remove all lower order regular terms in the expansion of the surface relative to the optimal plane. But more precisely, how do we build this thing? I mean, okay, in this specific picture, you could really take it to be the graph of W equals Z cubed. But in general, we need a good way to construct this object. And so in other words, you want to build a smooth submanifold over which you can reparameterize so that it exactly removes all these regular terms. So in other words, you want to construct a smooth surface that does this. So, and okay, how do you construct this in general? Well, the point is that so somehow the initial graphical approximation that I said one can get, that's essentially just, I mean, it's in some sense like a multi-valued epsilon regularity theorem, which is the best you can sort of hope for in general, that tells you that when your surface is, because as I said, you can't hope for Allard or De Giorgi when you have higher multiplicities, but you can hope to say that once your surface is close to Q copies of a flat plane, then it's well approximated by a Lipschitz multigraph with small constant. This graph will have Q sheets because if it's Q copies of the plane. And the surface really will agree with this graph away from a small closed set that you can quantitatively control. And so that's kind of, you can get that at sort of the starting scale, but this isn't so great at smaller scales. And I mean, so vaguely speaking, you want to, so you do this kind of Whitney type decomposition procedure that basically you want to take better and better graphical approximations to your surface at smaller scales, not just this sort of fixed one at the larger scale. So build local graphical approximations to the surface. At smaller scales. Then you want to start taking averages. So, okay, it depends whether if you're in the minimizing setting, essentially this center manifold will be constructed as a smoothed out average of the sheets of your surface. Take patch together smoothed out average of sheets of these, and right, and then I mean you want to check that this thing is really smooth. I mean, sure, you smooth it out, but you really, I mean, you want estimates that are not depending on this smoothing, because as I said, you're doing this sort of with a Whitney type decomposition that determines how much you have to localize in different places to build the graphical approximation there. So you really want sort of uniform regularity estimates on this sort of regularized average of the sheets. And the reason why you expect to really build something smooth in the end is, so this works in the minimizing case, morally because the average of the sheets should be close to a classical classical area minimizing surface in that case. Since of sheets is classical. Whereas in the so this essentially allows you to get Schauder estimates for this thing, because also you know that it's close to planar as well. On the other hand, for semi-calibrated things, you can't exactly just take averages of sheets. The problem with the semi-calibrated situation is that like the average of the sheets will be no better than C1 alpha in general. And indeed, so when I mentioned these examples, so yeah, like in general, you like almost minimizers, they don't have better regularity than like you should think of like a bunch of C1 alpha graphs superimposed, things like this. And so what you need to do, and you can also do this in the minimizing setting if you like, you can instead of for these local approximations, so instead of taking averages of these local approximations, you can still take the local approximations, the multi-valued ones to begin with. You can take the average of the sheets and prescribe it as boundary data at that local scale. And like on balls, for instance. And then you can solve the PDE that is associated to this, to being semi-calibrated, which I mentioned at some point coming from the first variation. And yeah, this tells you that, yeah, so then it's sort of those things that are giving you the center manifold in that case. So for semi-calibrated. And that also, I mean, that approach also works for minimizers, but you don't need it because you already have, yeah, you already have the PDE directly for the averages. Instead, build by solving PDE. Okay, so in the end, we're able to produce this nice smooth surface that we can reparameterize. We can reparameterize our multi-sheeted thing over. And now it should really be more reminiscent of this sort of ideal picture that I said that you should have. So now with reparameterizing over this and the manifold, we are closer to really looking at having a picture like sort of if this was a set to manifold, to really having like maybe this, and yeah, you really have that it's sort of some kind of average in some sense would be our draw, as you really want it to be. But unlike in this drawing, you don't necessarily expect that this thing actually passes through all of the singularities, right? You could have the sheets of your surface are all collapsing kind of elsewhere, because it's not exactly the average of the sheets. It's a more elaborate procedure, so they can collapse in other places. And so what one needs to do in general is, right, we want to, because as I said, we want to, in order to use this frequency function to reasonably control these singularities, we'd really like to have always at every scale, like this good picture of this center manifold, all of the sheets collapsing onto it, and then we can really hope to control things. But this generally doesn't happen. So generally, we do not have a good graphical approximation center manifold passing through, say, and center manifold passing through all well, not singularities, it's all the branch points nearby. I mean, for a start, already just this part alone, you can't hope. So if you think like this happens at the largest scale, that like the starting scale, right, where you knew that your surface was close to a plane. Already, this does not happen at all scales as we take R going to 0, right? Because remember, I mean, a priori, and I mean in general, even we don't know that we have uniqueness of tangent cones. We have some sequence of scales along which we know that we see this plane. And so we know that along scales comparable to that sequence, we can hope to keep having this condition that your surface is close to the plane, and then you can get the good graphical approximation. But if you look at, if this is your radial scale, in general, what happens is maybe you have your sequence RK, and so on. And so somehow you can start building sort of near here, you can start doing this whole procedure with this center manifold. And the point is that it will work well for as long as that graphical approximation and that center manifold are working well for you, which generally you have to stop at some point. And the only way that you wouldn't stop, so you could only keep going if, so we saw already in some other talks this notion of excess. So in this case, we're using tilt excess, which is kind of like at the level of these graphical approximations. It's a gradient excess. So it's an excess to optimal planes. So we could keep going if this tilt excess at scale R kept decaying quadratically, basically. That's kind of what you need in order for things to keep behaving well. But in general, that's not going to happen because, for instance, so, right, you always have to, because, right, we don't, I mean, in all these toy cases of these holomorphic curves, yes, because you have this like very concrete expansion of your surface, well, okay, even so, after subtracting the center manifold, so at least relative to the center manifold, you do have this. In general, we don't even know this. But also, right, in general, you always have situations like, again, this w squared equals z cubed, where here you don't have quadratic decay of your excess because, right, it's kind of determined by how the sheets are collapsing together. And so here they're kind of collapsing with order 3/2. Okay, so right, so the point is that you can keep doing this in some intervals of scales, and in general, these intervals you're going to have gaps between these intervals where you might not even have any graphical approximation, because maybe your surface, maybe here, your surface is not close to flat at all. Maybe. And so like that's where your excess just isn't even small whatsoever. And so essentially what one has to do, so for Armgren, for just the dimension estimate itself, it was kind of enough. So he called these kind of intervals of flattening, where you always had kind of a sequence of them. Maybe you had gaps in between, but somehow that didn't matter so much as long as you set things up well enough in these sequences. And then you could perform this blow up procedure that I was mentioning to boil to get the persistence of persistence of singularities result and sort of propagate the dimension bound up from the linearized situation. But for the structural theorem, this is where we have to do things a bit differently, and we basically optimize this kind of procedure with these intervals of scales where we build these graphical approximations. So what we have to do is we basically, so for the structural result, and this is where finally I can also bring things back to relate a bit to what I mentioned for these mod Q minimizers for this m-1 stratum piece. So for the structural result, what we basically do is we look more carefully at what is happening with these intervals of scales. And you can have kind of two situations. You can have uninterrupted strings of them where maybe, right, you had to stop here because, as I said, the key condition in order to keep going is having quadratic decay of the excess. So there are two reasons of how this could go wrong. Either it still decays, but too slowly. So here, excess decays too slowly, but still decays. Or there's the even worse case, as I said here, where it's not decaying at all. And what we do is we essentially use this Armgren's frequency function, which, okay, as I said, I mean, it's defined for graphs, but we're able to at least make sense of it at the level of, like, all we really want is the information it's giving us at scale 0. And the information it's giving us at scale 0 is the order of vanishing of this graph, which amounts to the order of collapsing of all of the sheets of the surface together. And we make sense of what we call a singularity degree. And I'll provide one more example but it's maybe already clear from the previous one I mentioned that showed the reason for the center manifold in the first place. To subdivide. So we define the singularity degree, which will be a number, and morally you should think of this number as like the value that Armgren's frequency function would give you if you knew that this was well defined, which from this whole picture, it's not clear a priori that it is. Well, I mean, this is all around a fixed branch point, right? So this is around a fixed branch point. And it's not at all clear that you have a well-defined order of vanishing, right? Because you have like these different these sequences of scales where you see your surface being close to flat. You have other scales where maybe it's not close to flat at all, right? So divide branch points. And kind of the first point is that it really is well defined. So actually, right, we define it a priori as the infimum over all possible blowups that you can take in these intervals where you do have you can set things up. And then we check that actually this infimum is the only value you ever get. So and part of that is checking. So so this is a number which is at least 1, because, right, it should be sort of the next order that you get. And already having, like, it's kind of the infinitesimal homogeneity of your surface relative to the optimal plane. Already having order exactly 1 is kind of counterintuitive, because right? It's like saying your surface is one homogeneous, but it's also not, like it's also, this is at a branch point. It's kind of, we don't have any examples of where this actually happens. But the point is that yeah, so for instance, the points of degree 1 will be exactly those where you do have these kind of gaps happening at arbitrarily small scales. And what we basically then, so maybe let me, in the last couple of minutes, just give one concrete example that's pretty similar to the last one. So for instance, if you consider W minus E squared, okay, I probably won't end up setting this up correctly. Okay, I'm not, so, okay, maybe I don't write this at the level of the surface itself, I'll just write it at the level of the behavior locally. I want to say that my surface is like WZ squared, Z to the 4, plus maybe you have a Z to the, maybe you have the same guy here. You can also have other terms, so maybe you have, I always need to check if, well, maybe I do. I think this is not divisible by 7. Okay, so you can have, right, you can have many orders in this kind of expansion, and the point is, so singularity degree picks up precisely this term. So you can maybe have even more higher order terms, but they don't matter. You just care about the first singular one. And yeah, the claim is that in general, this, yeah, you can prescribe this kind of value always, and it's always well defined, even if a priori we have to define it through this very complicated procedure as like an infimum of all possible sequences where you can run this compactness. And so in the end, the branch points, you can write them as the points of that have the singularity degree exactly 1, union the points where the singularity degree is strictly bigger than 1. And as I said, the singularity degree is really telling you like the order of collapsing of all of the sheets. And the nice thing is that here, it's also telling you, so how far above 1 it is tells you, so as long as it's like some discrete amount above 1, this immediately tells you that actually you have excess decay towards the unique flat plane, which is your tangent cone, with a small power law. And the power law is determined by precise, like, yeah, it's in terms of whatever this degree is minus 1. So it degenerates precisely in this case, and this is precisely the case where if we did have non-uniqueness of this flat plane at any branch points, they would be these ones. But here we know basically nothing. So here we don't have excess decay in general. I mean, we don't know. If we do, so at least not a power law. So maybe it's some weird logarithmic thing. We don't know, since we have no examples. But yeah, what you should take away from this is that, yeah, basically in the end, here, what we a posteriori get is that actually at these points, even if we have infinitely many such intervals, we actually never stop eventually. There's no gaps a posteriori. And so what this means is that we always have a reasonable graphical approximation. So here, reasonable approximation always. So for all small scales, even if it's changing. And this puts us in good shape to run this Neber-Valtorta rectifiable Reifenberg machinery that I mentioned, but not using mass ratios as the monotone quantity, now using frequency. As I said, so it also works in this kind of setting. We have to get around the fact that we have changing graphical approximations, but it turns out we have things set up in a suitably quantitative way that we get good control on how much they change. In this case, we have to use different techniques entirely, which are the same kind of techniques that are used for this m-1 stratum in the mod Q case. So here we use Leon-Simons, cylindrical tangent cones, approach, which, I mean, I'm exactly out of time, but just in 2 words, the idea is it's also in some sense an excess to K, only now it's not excess to optimal planes, it's excess to cones in a given class. And the cones for this class are superpositions of planes, because as I said, they're coming from the 2D picture. And so here at almost every point, what you would see at Hn-2 every point is you'd see a bunch of these planes meeting in a codimension 2 interface. And what we are able to show using this is that actually this set, even if it does exist, it's Hn-2 negligible, which is enough for the rectifiability. So yeah, this is what I mean. It's not then surprising that it's difficult to come up with examples of these. So they're going to start, so they don't exist in 2D. If they start existing, they exist in 3D. I mean, I've tried with some other people a bit to build things, but yeah, we really don't know anything beyond that. But at least for this structural result, it's enough. So yeah, that's all I wanted to say. So thanks.
The lecture, and are there questions, remarks? Okay, just curiosity. There is a hope that the set of singular of branch points has more structure. Maybe the pieces in the rectifiable pieces are like smooth or something like that.
So in general, no. So there are examples by Zhenhua Liu. I think I mentioned this at the end. So yeah, he's very good at building wild examples of things. So he constructs, you can prescribe fractal singular sets of dimensions below m-2. So you can prescribe basically arbitrarily bad fractal singular sets. So his so the singularity model that he's able to prescribe is always like a crossing type one. So it's not known if you can prescribe branch point fractal singular sets. That's still open.
Okay.
But I think, naively, I would expect that probably you can. It just needs some different approach.
Okay.
So yeah, in general, I'd say no, but yeah, maybe. Yeah, I mean, maybe for certain pieces you could, but I don't know. I don't have like a concrete statement in mind of what that would be. Yeah.
Okay. Thank you. Okay. If there are no other questions, we can thank the speaker again.